All right. What is up, everybody? Tom McGraw here with another episode in our Learn Rust Live series. Today, we'll be finishing up Chapter 15. We started it 2 weeks ago, took a break last week to install some new fresh carpet. Yeah. Used to be mucus green. We got a little gray action now going. We redid the other side here. Let's see if we can give it a little camera action. We got a little redo there. Got a little bookshelf upgrade going on. It's got the fresh. It's fresh. More to come. Stay tuned. But yeah, 2 weeks ago we did chapter 15. We started out. We learned about box. We learned about ref cell. We learned about reference counting. Did some stuff with cons lists. Today we'll be finishing that up, then moving on to chapter 16 if we have time, which is going to be kicking off concurrency, which I'm super excited about. Coming from other languages like Elixir, where concurrency is a primary feature of the language, I'm excited to see how Rust takes that on. It's a super powerful feature. We can leverage those cores in our computers that we all, have all these cores. Now we can start to use them. Hopefully your computer has a lot of cores. Maybe you don't. I don't know. But yeah, so we're gonna kick it off as we always do. You know what's coming. The plugs. And right there, the YouTube. Look at that. It's just like a sea of Rust. We have all the videos. If you've missed any videos, do not worry. No problemo. You're going to be able to find them all here. Chapters 1 through 15, first part of 15 covered here. We also did the Rustlings exercises. Definitely check that out if you want to see how to leverage Rust in some examples. It let us flex those muscles that we've been working out while we've been going through the book, so that was pretty awesome. We got a video here on Rust development with Docker, short little video, 14 minutes, much nicer than those 2-hour ones you've been used to. Check that out if you want to run Rust in a repeatable environment, so you don't have to install it on multiple machines. Maybe you got a laptop in your at your work, or maybe you have a computer if you're in school somewhere, maybe you have like a programmer room where you have a bunch of school computers. Maybe you're on your friends and they're like, what's this Rust? What? Don't install that. And you're like, relax. We're gonna use Docker. I'm gonna install Docker. But after that, I got my repeatable Rust environment. Check that out. More one-off content to come. I've been meaning to put more up. Have not gotten around to it with some stuff that's been going on, renovations and so forth. But more to come. Also, we have some stuff we've done before. Live coding. We did a serverless API with AWS Lambda. We used TypeScript for that, DynamoDB, so that's pretty cool if you've ever been looking to get into serverless and you're wondering what's this serverless thing about. How do I use AWS Lambda? Check that video out. It's a good introduction to that. And then before that, we did some React Native stuff, which was really fun. I'm a big JavaScript fan. I built a couple React Native apps that I've put into production for companies that I've been at, and it's a fantastic technology. We also tried out Recoil.js for that. I'm going to revisit Recoil as well. It's had some development since we first kicked it off pretty early on in its life cycle, but we'll revisit that, see where it's come. So today, what are we going to do? Chapter 15, we'll wrap it up. Check out the Twitter. You'll get updates from when I go live. All the stuff we do here today will be going up on our GitHub repo. It goes under Learn Rust Live. Click in here. You got projects. And in here, we got all our chapters. There's the chapter we just did. Check that out. You can follow along. You can pull it down. You can start your own repo. Whatever you want, it's there if you need it. As always, we do this at the beginning of every stream. If you've been watching or you've been following along on YouTube, we do this. We always got to give a shout out to Steve Klobnik, Carol Nichols, and everyone from the Rust community that contributed to this amazing book. We wouldn't be able to do this without this book. It's been fantastic. I always say, you've heard me say it if you watch these videos, I usually like to jump right into a language. Everyone recommended, if I'm going to jump into Rust, to dive into the book first, because there's a lot to learn, right? We've seen that. There's a lot of concepts. And now we may not use all of them day to day, but it's good to have a basic understanding, and it's been very helpful, especially since this is a different style language than what I'm used to. I write in JavaScript every day, Python every day, Elixir, but I'm not dealing with systems programming. C is something I haven't written since school, so it's been really interesting, and the book has been really helpful. So shout out again to Steve Klobnik, Carol Nichols, and anyone from the Rust community that has contributed. Really appreciate it. All right, so today we're going to be continuing chapter 15. I want to do a brief recap because we did a lot. we went through a lot. And so I want to go over kind of where we left off because we're picking up mid-chapter. We're picking up in the middle of the ref cell chapter. And so there's a section here I just want to go over because it talks about what we covered with reference counter, box, and ref cell. So here's a recap of the reasons to choose box, ref cell, and reference counter, right? So reference counter enables multiple owners of the same data. Box T and ref cell have single owners. So ref cell again is used for multiple owners. We saw an instance where we had a cons list spread across multiple owners. So you had a cons list that contained a cons list that was created by a different owner. So that's what we're going to use reference counter for. And then you have box T. Box T allows immutable and mutable borrows checked at compile time. Reference counter allows only immutable borrows checked at compile time. And then ref cell has the benefit of allowing immutable and mutable borrows checked at runtime. So because ref cell allows mutable borrows checked at runtime, you can mutate the value inside the ref cell even when the ref cell is immutable. So let's go over that again. Because the ref cell allows mutable borrows checked at runtime, not compile time, you can mutate the value inside the ref cell even when the ref cell is itself immutable. So pretty cool stuff. All right, so this is the last thing we talked about, interior mutability, a mutable borrow to an immutable value. And so where we left off was we had created this source lib where we were writing a program and trying to figure out what is the use case for ref cell. And so what we determined, or what the book told us, is that it's really good for testing. It's really good for mocking because there's no built-in way to mock. So we can use ref cell to do that. And the example that they've used here is we have a messenger, a limit tracker, and so our limit tracker has a new and a set value, right? Hold on one second. What? Sorry about that. Got a message. All right, so we have the messenger, which has a send function, limit tracker, and so our limit tracker has this messenger here, has a new function to instantiate it, and then we had this function called set value. Set value equals value, percentage of max, self.value as f64, self.max as f64. And then we have a check here. If percentage of max is greater than or equal to 1, we send this message. Else if percentage of max is greater than or equal to 0.9, we send this one. Else if percentage of max is greater than or equal to 0.75, we send this one. And so the key thing here is they mention messenger trait has one method called send that takes an immutable reference to self, and that's here. So send takes an immutable reference to self. But in our test that we did, we want to be able to create a messenger with this value called sent messages to keep track of the messages we're sending. And that's what we're testing. We're saying we're not testing what happens when we try to send it. We just want to test that when we set a limit or set a value, that those messages are sent. And so what we're doing is we're just storing the sent messages in a vector. So here you can see we have a limit tracker, mock messenger, and we have our mock messenger here. It has sent messages. And remember, the function here, the limit tracker, takes a reference to an immutable mock messenger. And so that wouldn't work. And we can see here when we tried to compile that, it said it's a reference, so the data refers to cannot be borrowed or mutable. And the way we get around that is we wrap that vector in a ref cell, which allows us to use this function here and mutate that vector. So pretty interesting stuff, what's happening there. All right. So that's where we left off. Last change so we did this. This is basically the last part we did. The last change we have to make is in the assertion to see how many items are in the inner vector. We can borrow on the ref cell vec string, get an immutable reference to a vector. So that's where we left off. I'm going to pull that up in the code. So let's see what we got here. And let's go ahead and I'm going to go into this project. So I'm going to do projects, chapter 15. Ref cell. Let's open up a new window directly to that. Get rid of that. All right. We're going to update our Rust analyzer, which I've been using. It's been pretty great. So I'm going to go ahead and move out of your way and run this code so you can see what it looks like. All right, so we're going to do cargo run. Oh. Cargo test. Oh, because we're using a library, right? So you can see here, oh, we have some other code here that's probably allowing it to not run, which is this function down here, because we have a main function. But what we actually just want to test is that it compiles. So what we can do is cargo check. This is the part that it's not letting me compile. So I'm just going to comment that out. And you can see everything else compiles. We just get a warning. So that worked out. And that's because we were able to use this ref cell. So the next part is figuring out how that all works. And again, if this recap was kind of quick, don't worry. It's all covered in the previous video on YouTube. So you can just fast forward to the end, get to the ref cell section and go over it again. Watch it on 2x speed. But so today we're going to, we're not going to go over this too much. We're going to go over how it works. And that's where we left off. So we're going to be picking up right here, keeping track of borrows at runtime with refcelt. So again, the benefit of refcelt is it allows you to borrow something that's immutable in a mutable way. And it's unsafe Rust. We learned about that as well. Okay, keeping track of borrows at runtime with refcel. When creating immutable and mutable references, we use the ampersand and the ampersand mute syntax respectively. With refcelt, we use the borrow and borrow mute methods, which are part of the safe API that belongs to refcel. So the borrow and borrow mute, and we're doing that here. You can see online here, we have sent messages. We borrow it in a mutable way so that we can push those messages onto it, right? The refcelt keeps track of how many reft and ref mute smart pointers are currently active. Every time we call borrow, the refcelt increases its count of how many immutable borrows are active. When a reft value goes out of scope, the count of immutable borrows goes down by 1, just like the compile time borrow rules. Refcelt lets us have many immutable borrows or one mutable borrow at any point in time. So it can have many mutable borrows or one mutable borrow at any given time. And we try to violate these rules. Rather than getting compile error as we would with references, the implementation of refcel will panic. So that's the difference. Because it happens at runtime, it can't tell us at compile time that there's something wrong. So we'll get a panic at runtime. And that's why I'm kind of sensing that it's useful for testing, but maybe not something you would use in your regular running code or your library. So testing, it's okay, right? You're going to run the test. If it breaks, if it panics during the test, that's something you can assert, but it's not something you would maybe put in your code. But maybe I'm wrong. We'll see. So if we try to violate these rules, rather than getting compiler errors with references, it would panic. And so down below, it shows a modification of the implementation of send. We're deliberately trying to create 2 mutable borrows active for the same scope to illustrate that refcel prevents us from doing this. So here they have 1 borrow, 2 borrows. So they're trying to borrow mutable twice, and then they're trying to mutate it, right? They're trying to push something onto it. And you can see here, so they create the 2 variables, they try to borrow it, and it throws an exception. And the exception that it's going to throw is panicked at already borrowed borrow mute error. And then it tells you, look at these messages. Awesome. Run with the Rust environment variable to display a backtrace. But this is the key thing. Already borrowed. So notice that the code panicked with the message already borrowed. This is how refcelt handles violations of the borrowing rules at runtime. So again, it's going to panic. If we're using box, it's not, right? Because that's going to be a compile time. If we're using reference counter, it's not. And so refcel is similar to box in the way that you would use it, right? But you're going to get that benefit of it's going to work at runtime for refcel, so it's great for tests when you want to do things, whereas box will give you that at compile time. So you probably want to lean towards box if you can, and only use refcel when you absolutely need it. Okay, caching borrow errors at runtime rather than compile time means that you would find a mistake in your code later in the development process and possibly not until your code is deployed to production. There you go. That's exactly what we just said. Also, your code would incur a small runtime performance penalty as a result of keeping track of the borrows at runtime rather than compile time. So small runtime penalty as well. However, using refcelt makes it possible to write a mock object that can modify itself to keep track of the messages it has seen, which is what we're doing here, right? So it keeps track of the messages that it has seen and it allows us to mutate it, right? So that's pretty Pretty great. So we can write, let's see, how to seem while you're using it in a context where only immutable values are allowed. And why do we say that this is a context where only immutable values are allowed? Well, that's because we've specified that our, where is it here? Our limit tracker takes a messenger, right? And our messenger, the set value is mutable, self, right? So we're passing it self here, and we have messenger. We haven't declared messenger as mutable. So it's a reference, right? And so that's why we need this ref cell. Pretty cool. Having multiple owners of immutable data by combining reference counter and reference cell. So remember, reference cell has the ability to have multiple owners. I'm going to quickly show that because I think that's important. It is important. Otherwise, we wouldn't be doing it, right? And so that is here. Let me just open that up. All right. All right, so let me show what we were talking about here. So if you remember, we had that cons list. The cons list again was an item. It's a tuple where the first item is the item and the second item is the rest of the list and so forth, and it's recursive like that. So we used reference count to demonstrate multiple ownership. So you can see that we have this A, this cons list, and it looks confusing. It looks Lisp-like, right, with all these parentheses. But what's happening here, if you break it down by parentheses, you have your number here. This is the first item, and the other item is the rest of the list. And you can see that the rest of the list looks like the beginning. That's because this is a recursive structure. So you have your 32-bit integer, and then you have another list with a 32-bit integer and the rest of the list. And in the case of the list n, we use nil. But so the reason we're talking about multiple owners is you can see B references A, right? So B is taking ownership of A here, and C is taking ownership of A as well. And so that's the multiple owners. And that's why we had to use RC instead of box, which we used previously when making the cons list. Again, if it's confusing, it's all covered in the beginning of chapter 15. So go back, read that chapter, get a refresher, or check out the video where we did it on YouTube. That's probably the best way to do it. Or just pop back and read it. It's a quick chapter. We usually take longer to go through the chapters because we're talking through it and doing exercise. So reading it's probably the quickest way to get the recap. But I love the views. You know? I don't mind views, you know what I'm saying? All right, so let's go into this here. So again, a common way to use ref cell is in combination with the reference counter. Recall that reference counter lets you have multiple owners of the same data. We just saw that, but only gives you immutable access to the data. If you have a reference counter that holds a ref cell, you can get a value that can have multiple owners and that you can mutate. So you're like, you're a wizard. You're a Rust wizard. People are coming up to you, calling you Gandalf, you know, Gandalf the Rust station, whatever. For example, recall the cons list example. We just did that. We just recalled that, right? Where we used reference counting to allow multiple lists to share ownership of another list. Because reference counter holds only immutable values, we can't change any of the values in the list once we've created them. Let's add in ref cell to gain the ability to change the values in the lists. All right, so let's go ahead and crank this out. So what we're going to do is we're going to get rid of that for a second. We're going to go to our main here. Let's see, where did they put this? Oh no, they put this into, now they're actually using this here. All right, so let's go ahead and I'm going to comment this out. Actually, yeah, I'll comment this out and I'll just say using a RCT with a ref cell T to gain a, basically we want something that can allow multiple owners and still be mutable, right? Allow for multiple owners and immutability. And what I'm going to do here is for myself, I'm going to reference this part of the book as well. So I'm going to click that. I'm just going to go ahead and copy it. This way I can see in my comment what section we're talking about. I think that's pretty useful, right? Okay. So here, let me see what's changed. So we have derive debug on our list. Let's go ahead and add that. Again, that's so that we can print out the debug. So we do hashtag derive debug. There we go, auto completion. We have our cons list. We're going to modify this a bit. So what I'm going to do is I'm going to comment this out. I'm going to go ahead and put the same comment here, up here. Let's go ahead and get rid of that, and then we're just going to do enum list. So we have our list enum, and it's cons list with the RC, and so in here, the generic type of the reference count is going to be ref cell. That's interesting. And it's going to be ref cell of I32. And then the second part of the tuple, right, the second item is going to be a reference count list. And then nil to represent when it's empty. So you want to specify that your enum can be of type nil because that's how we reflect the end of the list, right? So in the crate, they're importing cons nil, we have that. Standard reference counting RC, and then we need to import use standard cell ref cell. Okay, and then in our main, we're just going to go ahead and type. Let me move this. So I can scroll down a little bit. Okay, so then in our main function here, we're just going to do let value equal RC new, and then we're going to instantiate a ref cell in here using the same kind of syntax, new, and we're just going to put an I32 in there. I32. And then what we're going to do is we're going to say let A equal RC new, and we're just copying what I'm seeing here. RC new. And here we're going to create our cons list, and the first value is going to be RC clone, a reference to value, so we're calling clone there. Again, that's how we take the ownership, right? We use clone for that. Value, and then RC new and nil to represent the end of the list. So our list A is pretty short. It's just this one item, which is a reference counting clone of this value, which is a reference counter containing a ref cell. Whoa. Whoa, where did we go here? Oh, that's cool. It took me to the definition. Okay, so now we have A. So A is pretty short. Let me see. I probably missed a parenthesis here. What is it saying? It says add here. Oh, it's probably because I forgot. Let's see. Let A equal RC new, cons, RC clone, value, comma, RC new, nil. It should be right. Let's keep going. See what happens. It's because I didn't save. All right, so now B is going to contain A. So B equals cons, RC new, ref cell new, 3. So that's the first value. It's just going to contain 3. And then it's going to have RC clone, and we're going to clone, and we're going to grab a reference to A. And then we're going to tidy that up. And now what we'll do is we'll just copy B. We're going to change it to C. And instead of 3, we're going to make that 4. And we're going to leave this as A. So let's just go over this, right? Because it's a lot of parentheses, a lot of news. Let's just cover what's happening, because it's not too bad if you can kind of group this together in your mind. It looks like a lot of code, but it's not too bad, right? Because, oh, sorry, we got a little water spillage here. If you can group this in your mind a little bit and target the key points, I think it makes it a little bit simpler. So what are the key points? The key points are the center of the parentheses that we're looking at here, and then we'll work our way out. So if we look here, what is the center? Or let's start here better. We have 5. So we have 5. And we could just say value equals 5, but we're not. So let's move out one at a time and see what we're dealing with here. So instead of just using 5, we're using a ref cell of 5. Why? Because with the ref cell, right, we're going to have that functionality we want, that indirection. So the ref cell is going to allow us to, in our case, the whole reason we're doing it, right, is because if we use ref cell in combination with reference counter, it's gonna only give, so it's gonna allow us to have mutable access. So here you can see that recall that reference counter lets you have multiple owners of some data, but only gives you immutable access. If you use reference counter that holds a rest cell, you get value that has multiple owners and you can mutate. So we're using rest cell to make this mutable. So again, we start in the middle. So we start with the 5. The 5 is a 32-bit integer. Work our way out. Why are we using rest cell? Because we want it to be mutable. Why are we using reference counter? Because we want it to have multiple owners. So we're adding functionality by nesting these functions, right? Okay, so that's what we have for value. So what do we have now? With value, we have an unsigned, or in this case, signed. Yeah, I32. It says it right here. It's a signed 32-bit integer that can be mutated and can have multiple owners because it's wrapped like this. Good. All right, so we know what value is. So now let's go here, and again, let's start in the center. Let's first look at this one in the center, nil. Why nil? Because it's a cons list, and nil represents the end. Why reference counter to nil? In this case, it's similar to box. It's because we don't know the size at compile time. But just for the sake of this, we can say we're using reference counter nil because we are dealing with something that can have multiple owners, right? But really what it's being used for here, it's being used similar to box. But because we're going to allow it to be owned by other lists here, we need to make it a reference counter instead of a box. Okay, so that's nil. Value. So again, we know that value is a mutable signed 32-bit integer that can have multiple owners. We're cloning it. So we're just cloning that value. And we're popping that into a new reference counter so that it can have multiple owners. All right? So now we know that A as a whole contains that value and nil, and because it's using reference counters for those properties, it itself can have multiple owners. We're good? We're good. Let's move on. Again, let's start right in the center. Let's start with this one. 3. This is the same thing as up here. So this is going to give us the mutability, and this is going to give us the ability to have multiple owners. All right, let's go here. We know that A is this here. It can be mutated, and it can have multiple owners, and so we're cloning it. We're cloning A. So now B is a cons list that contains this. It contains a 3 that is mutable and can have multiple owners, and it contains a clone of A here. So we're seeing now that A has multiple owners. We see that value also has multiple owners, but now we see that A has multiple owners. And who are the owners? B. And you can see C is basically the same with just a different integer. So C is also an owner. Not too bad. It's a lot. It's a lot to look at. I'm hoping I don't have to write this every day. I'm not gonna lie. This is not my favorite part. But I feel like once we get a use case for it, it'll come up and we won't be totally confused. We'll understand what's happening. We're gonna see this at some point in code or source code, or we're gonna, you know where we're gonna see it. You all know. You're like, I'm gonna see it on Stack Overflow. I'm gonna Google for something, and someone's just gonna be like, use reference counter. It's so easy. Just use ref cell. Now you're gonna go in and be like, yo, I know what that is. I didn't know I needed it, but I know what that is. I don't need to ask follow-up questions, right? So pretty cool. All right, back to the book. Hopefully that part's clear now, at least. Okay, so let's go in a little bit. We have our here, and then we want to add this part here. So we got to just add below. We're going to do value.borrow mutable. Again, we have to borrow mute, right? Because we're dealing with a ref cell. We have to use borrow mute. And we're going to say plus equals 10, which is the same as saying value borrow mute. It's the same as saying value equals value plus 10, essentially, right? And so what is happening here? This one is we are borrowing the value in a mutable way, and then we have to dereference it because, again, remember the value is a reference, right? So we have to dereference it to get the actual value, the actual thing that the pointer points to. And again, because reference counter is a smart pointer, ref cell is a smart pointer, box is a smart pointer, they all implement the deref trait, which is going to allow us to use that asterisk to dereference it, right? If it didn't implement the deref trait, that wouldn't be possible. Look at us. Look at us. Who would have thought? Not me. All right, so then let's print this. I'm just going to copy this because I don't feel like writing print statements. And I'm sure you don't want to watch me. Okay, so let's save that. And let's just cargo run it. Let me get out of your way. Classic Tom. Cargo run. Bam. A after equals cons ref cell 15, because again, we're adding 10, remember? B after 3, C after, because we didn't actually mutate. We mutated value, but these were clones, right? These were clones of value. That's why they weren't modified. Pretty cool. And I'm sure we're gonna read all about it right now. So let's see what that looks like. Sorry, my nose is itchy. Okay. So we create a value that is an instance of reference counter ref cell I32 and store it in a variable named value. We dug through this, so we can access it directly later. Then we create a list in A with a cons variant that holds value. We need to clone value so that both A and value have ownership of the inner 5 value rather than transferring ownership from value to A or having A borrow from value. We kind of dove into it. That's basically just restating what we went over in the code. We wrap the list A in a reference counter so that we can create lists B and C. They can both refer to A, which is what we did. So again, allowing to have multiple owners, that's all that is. After we created the lists in A, B, and C, we add 10 to the value in value. We do this by calling borrow mute to get a mutable borrow of that on value, which uses the automatic dereferencing kind of feature that we talked about already in chapter 5 to dereference the reference counter to the inner ref cell value. The borrow mute method returns a ref mute smart pointer, and we can use the dereference asterisk operator on it and change the inner value. So we just talked through that. That's basically just restating more fancily. Like, I'm not a book author. I could be. It could happen. It won't. No, I don't have time for that. That's why we're thanking these authors at the beginning of every session, because they've put in this time. They've worded it so beautifully like this. But here's the thing that's key for us, right? When we print A, B, and C, we can see that they have the modified value of 15 rather than 5. 15. So if you see that value is 15. We saw that. 15. So value got modified. These values didn't because we didn't change those. We changed value. So that's pretty key. This technique is pretty neat. It's pretty neat. By using ref cell, we have an outwardly immutable list value, but we can use the methods on ref cell that provide access to its immutability so we can modify our data when we need to. The runtime checks of the borrowing rules protect us from the data races, and it's sometimes worth trading a bit of speed for this flexibility in our data structures. The standard library has other types that provide interior immutability, such as CellT, which is similar except that instead of giving references to the inner values, the value is copied in and out of the cell. There is also MutexT, which offers interior immutability that's safe to use across threads. We'll discuss them in chapter 16. Check out the standard library docs for more details on the difference between these types. All right. So now we're going to talk about reference cycles can leak memory. I don't want to leak memory. Rust's memory safety guarantees make it difficult, but not impossible, to accidentally create memory that is never cleaned up, known as a memory leak. If you've written JavaScript, you've dealt with this. You may not have noticed you dealt with it, but when you're like, absolute, probably a memory leak. Preventing memory leaks entirely is not one of Rust's guarantees in the same way that disallowing data races at compile time is, meaning memory leaks are memory safe in Rust. We can see that Rust allows memory leaks by using reference counting T and ref cell T. It's possible to create references where items refer to each other in a cyclical way, right? This creates memory leaks because the reference count of each item in the cycle will never reach 0 because they reference each other, and the values will never be dropped. Creating a reference cycle. Look at how reference cycle might happen and how to prevent it, starting with the definition of list enum and a tail method in listing 1525. Let's type this up. So I'm going to go ahead and create another project here. Let's do cargo new memory leaks. This is dangerous, right? All right, let's go back here. Okay, so we have memory leaks, we have source main. Let's go ahead and copy this. Let's type it out. So we have, I'm just gonna copy these imports first. Get rid of that. All right. And then we're going to go ahead and put derive debug. Comes for free there. Enum List, and we're dealing with the cons list again. Cons I32, and then a ref cell containing a reference counter. All right, and then nil to represent the end when we get there. And then we're going to implement a function called tail on list. And so that function tail is going to take a reference to self, and it's going to return an option type. The option is going to contain a reference to ref cell RC list. And we're going to do a match on self. Cons, so if we get a cons list, we're going to grab the item and return some items. So we're just going to fulfill this option. And then if we get nil, we're just going to return none. And then our function main will just leave it as print hello world. What does this say? Variance never constructed, that's all. All right, so we're using another variation of the list definition from listing 15.5. The second element in the cons variant is now ref cell reference counting list, meaning that instead of having the ability to modify the unsigned 32 or the signed 32-bit values as we did in listing 15.24, we want to modify the list value. We want to modify which list value a cons variant is pointing to. Okay. We're also adding a tail method to make it convenient for us to access the second item if we have a cons variant. So the tail being the rest of the list. Now, if you've ever dealt with cons lists, this is a very common use case. The reason a cons list is useful is because you can destructure it into two parts, the head of the list and the rest of the list. This makes doing things like recursion really easy. You could imagine you have something that is supposed to operate on each part of the list. Maybe you just want to print each item in the list. You could have a loop over each item in the list, or you can have a function that takes an item and the rest of the list and prints the first item. Then you can do a check. If the second list is empty, you know you're complete, and you can just call that in a recursive way. Languages that do this, for example, would be Clojure, makes it easy. And Elixir has a really nice pattern matching cons list kind of combination for doing recursion. So it's a very powerful thing. And that's why the cons list is useful, because you can get that head and that tail. And so that's what we're doing here. We're saying this is going to ignore the first. We don't care about the head. We want the rest of the list. And that's what tail is. Just grabbing that second part of the list. Pretty cool. Okay. So we're using that variation that has tail that gets us the second part. In the listing below, we're adding a main function that uses the definitions in the previous listing. This code creates a list in A and a list in B that points to the list in A. Then it modifies the list in A to point to B, creating that cycle, right? There are println statements along the way to show what the reference counts are at various points in the process. All right, so let's go ahead and make this happen. So we're going to go ahead and I'm going to type this up. If you're on YouTube, feel free to fast forward. If you're in the stream, hang around. But I think it's just good practice to type this stuff. So we're creating a cons list starting at 5, and the second item is a ref cell new with a reference counter pointing to nil. So this is like the last item in the list, right? Okay, and then we have some prints, and we're just going to copy the prints. Actually, I'm going to type this one because I want to learn about strong count. Typing always helps me. So we have a initial RC count equals, so the reference count, right? RC strong count, which again gets us the count of the references. So we should see that it's only one here, right? And then println a next item next item, and we're going to use the derive debug here to print out it like that, right? And we're just going to do a.tail. Oh, why is that not working? There we go. A.tail. Perfect. Then we're going to create B, and we're going to do B as an RC new cons, which contains 10. And then instead of containing nil because we're going to actually reference A here. So we're going to do ref cell new, and we're going to contain a reference counter clone where we're going to clone A. All right. And then we're just going to print these. I'm just going to copy this now at this point. So here we're printing the RC count after B creation. Again, we have another reference to A, so we should see 2 at that point. And then initial count of B should be 1. And then B next item. And now here's where we're going to get interesting. We're going to say, we're going to mutate A to actually reference B. So we're going to say if let sum link equal A.tail. We're going to dereference link.borrow mute. So we're borrowing in a immutable way. So again, this is if sum link, right, equals A.tail. So we're saying A.tail returns an option, right? We can see that here because it could return nil if it's empty. So we're saying if it doesn't return nil, if it exists, right? If let, we saw this sum A.tail, we're going to we're going to capture A.tail as link. And then we're going to try to grab link in a mutable way. We're going to dereference it to get the value. We're going to modify the value. What are we going to make the value? We're going to make the value of reference to B. And this is going to cause all sorts of problems. And then I'm just going to print this. And so we're going to see what the count is. And then here you can see they have this comment here. It says uncomment the next line to see that we have a cycle. It will overflow the stack. I'm definitely going to do that. Definitely going to do that. Let me just post it here. So first, let's just see what we print out as it currently is, and then we'll uncomment that line. And I almost cursed on the stream. That's all right. Then we're going to comment that line out and see it blow up the stack, which is always fun, right? All right, so let's go to bottom left here. Let's save that, and let's go ahead and cargo run. Great. What did I mess up? So we have cannot find function tuple struct con. I messed up. And I misspelled a bunch of stuff. So cons strong count. There we go. Clear that out. Make it a little bit bigger here for y'all. Cargo run. Okay. So let's go over what we see here. So A initial count is 1. That's because here we've created a reference to it, right? A.next item is the end of the list. A.reference count after B creation is 2 because B has a reference to A. B initial count is 1. B's next item is a reference to A, right? B RC count after changing A equals 2. So we change A to reference B. So now something references B. A still has 2 because nothing else is referencing A. Now let's uncomment this. Bam. Woo! Overflowed the stack. Let's go. Look at this. Pretty cool. That's probably not great, right? So we create a reference count list, instant, right? Holding a list value in the variable A with an initial list of 5 and then nil. We then create the reference count list instance holding another list. So we did that. We print it out. We see here exactly what we got. And when we uncomment that, we see it blows the stack. The reference count of the reference count list instances in both A and B are 2 after we change them. Russ will try and drop B first. So at the end of main, Russ will try to drop B first, which will decrease the count of the RC list instance in B by 1. However, because A is still referencing the RC list that was in B, that reference count list has a count of 1 rather than 0. So the memory that the RC list has on the heap won't be dropped because there's still somebody using it, right? And we know that it won't get dropped till everyone's done using it. It's like the TV, right? If there's a TV on a room and multiple people are watching, that was the analogy they gave. Someone doesn't just come in and be a savage and just shut off the TV while people are there, right? I mean, it happens. It happens, but not supposed to happen, right? So that's what's going to happen here. It's going to still have that 1, which is going to cause the issue. So it has it on the heap and it won't be dropped. The memory will just sit there with a count of 1 forever. To visualize this reference cycle, we've created a diagram. Look at this beautiful diagram. Art. This is art. Its finest. So we have A, which is a list with 5. Its second item is a reference to B, which has 10, but it references A cycle. See, it's cyclical. That's what we're talking about here. So if you uncomment the print line, we see that it blows up the stack. In this case, right after we create the reference cycle, the program ends. The consequences of this cycle aren't very dire. However, if a more complex program allocated lots of memory in a cycle and held onto it for a long time, the program would use more memory than it needed and might overwhelm the system, causing it to run out of available memory. You've all had your computers go like they're taking off. The fans are running. It's like all that memory usage. This thing would be a big problem, right? Ugh. Creating reference cycles is not easily done. That's good. It's basically saying if you create one of these, you're kind of a clown. I'm a clown though, so. Creating reference cycles is not easily done, but it's not impossible either. If you have ref cell values that contain ref count values or similar nested combination of types with interior immutability and reference counting, you must ensure that you don't create cycles. You can't rely on Rust to catch them. This is going to be on the programmer. And that's okay. If you've, again, I come from other languages. I know maybe some of you, maybe this is your first language. We know what we're doing. We haven't always had this safety. We're coming to Rust for its safety. So hopefully we have this kind of experience. And if not, it's just something to look out for. And that's what they're calling out here. So pretty cool. We have to ensure that we don't create cycles. You can't rely on Rust. Creating a reference cycle would be a logic bug in your program that you should use automated tests, code reviews, and other software development practices to minimize. So stuff that if you're a developer, you're familiar with. If you're learning to be a developer, you're getting familiar with. And if you aren't familiar with these things, you will over time. You're here for a reason, right? You're learning. Big ups to you. Another solution for avoiding reference cycles is reorganizing your data structure so that some references express ownership and some references just don't. As a result, you can have cycles made up of some ownership relationships and some non-ownership relationships. And only the ownership relationships affect whether or not a value can be dropped. In listing 1525, we always want cons variants to own their list. So reorganizing the data structure isn't possible. Let's look at an example using graphs made up of parent nodes and child nodes to see when non-ownership relationships are an appropriate way to prevent reference cycles. So non-ownership relationships when we don't need them to own it, like we did with the cons list where we had ownership. Okay, preventing reference cycles, turning a reference counter into a weak. All right, let's see. So far, we've demonstrated that calling reference count clone increases the strong count of a reference. And that's what we've been doing. Because we want ownership. So that's why we've been doing that. So it increases that reference count. It increases the strong count of the reference counter instance. And a reference counter instance is only cleaned up if its strong count reaches 0. What does that mean? It means it only is cleaned up if no one owns it anymore. If everyone that was owning it or using it is out of scope. The function that those things lived in has ended. They've moved on. They've trickled that strong count down to 0 and it can be cleaned up. That's what that means. That's it. You can also create a weak reference to a value with a reference count instance by calling reference count downgrade and passing a reference to the reference count. When you call reference count downgrade, you get a smart pointer of type weak over the generic t. Instead of increasing the strong count in the reference counter instance by 1, calling reference count downgrade increases the weak count by 1. So now we see why it's called strong count. It's not just cool. It's not just because strong count sounds cool. I thought it was. It's not. It's because there's also weak count. It's pretty interesting. So it uses weak count instead of strong count. Instead of increasing the strong count in the reference count by 1, increase the weak count. The reference count type uses weak count to keep track of how many weak references exist, similar to the strong count. The difference is, this is key, the weak count doesn't need to be 0 for it to be cleaned up. So I'm thinking, this is what I'm thinking. I'm using that TV analogy again, right? So we said that a strong count is like you have the TV's on, right? And there's a bunch of people watching the TV. The TV can't be turned off until everyone's done watching it, right? Everyone leaves the room. They're like, I'm good. Shut it off. We're gonna go out to dinner. I'm thinking like this, right? A weak reference is the person that's low-key in the room with the TV, but they're reading a book, right? They're not really paying attention to TV. They're in the room. You have on your show. Maybe you're watching some show, Cobra Kai or something like real sick, or maybe you're watching whatever you're watching. This person's in the room, but they're reading a book, right? Maybe they have their headphones on. Maybe it's like the kid on the iPad. Weak. They don't care. You shut off that TV. They won't even notice, right? They're like, yeah, I'll be in the room, but don't worry about me. I'm not really watching. That's what the weak is. That's what I see the weak as. Look at, you're getting the best analogies here. That's why you come. That's why you're here, right? Okay, strong references are how you can share ownership of a reference count instance. Weak references don't express an ownership relationship. They won't cause a reference cycle because any cycle involving some weak references will be broken once the strong reference count of the value is about to 0. So once all the folks watching, actually paying attention to the show are done watching the show, they can turn it off. Weak count won't be affected. They'll continue reading their book, whatever. Because the value of the weak T references might have been dropped to do anything with the value of weak T is pointing to, you must make sure the values still exist. Okay, that's key. Because the value that weak T references might have been dropped to do anything with that value, you must make sure the value still exists. So it's kind of like you need to check. You need to look up from the book to see if the TV's on before you try changing the channel, because you don't even know. You haven't been paying attention, right? Do this by calling the upgrade method on a weak T instance, which will return an option reference count T. You'll get a result of some of the reference count value has not been dropped yet, and a result of none if it has been dropped. Because upgrade returns an option reference count T, Rust will ensure that the sum case and the none case are handled, and there won't be an invalid pointer. So it'll make sure, because you're handling it as an option, right? Because it might not be there. That's that maybe instance, right? The possible presence of something. So that's pretty cool. As an example, rather than using a list whose items know only about the next item, we'll create a tree whose items know about their children items and their parent items. All right. Creating a tree data structure, a node with child nodes. To start, we'll build a tree with nodes that know about their child nodes. I'm just going to do this right in the same file. Shouldn't be a problemo. So again, we're going to create a tree, right? This tree, so like a branch, right? With nodes that know about their child nodes. So it's a tree going downward, like roots, right? We'll create a struct named node that holds its own signed 32-bit integer value as well as a reference to its child node. So if you're drawing it, you can think of, you have a node holding a value. So I'm going to hold my tech deck, any excuse. And then it has a reference to the child node. So maybe there's other nodes down here. So it has its own value and then a pointer to all of its child nodes. If you're familiar with trees, this should be a regular concept. If you're not, quick Google. That's it. It's easy. Lots of different kinds of trees. Okay, so let's go ahead and do this. So we're going to first do, we're going to make sure we have ref cell. We do have ref cell and that. We're all good there. And so what we're going to do is we're going to do derive debug. Actually, you know what I'm going to do? Because I want this to be kind of compartmentalized. I'm going to save this. And I'm going to go ahead and just create a new one for, we're going to call it weak. Cargo new, weak. We'll call it weak references. Pop that open there. There we go. All right, so now we have a fresh, just start from, just to have it nice and compartmentalized for the repo. Okay, so we're gonna go ahead and import those, use standard cell and ref cell, pull in RC, and then we're gonna do derive debug so that we can log it. And we're gonna just find a struct called node. It's gonna contain a value that's an assigned 32-bit integer and children, which is gonna be a ref cell vector containing ref cell containing a node. All right, so what do we have here? We have a node that contains a value and then a pointer to its child. What is its child? Well, its child is a ref cell. Well, we always start in the inside, right? That's easiest. So it's a node, so its child is another one of these. But we've wrapped it in a reference counter so we can have multiple owners, right? we wrapped that in a vector. So it's children because there can be many children. So there can be many nodes that can have multiple owners. And we wrap that in a ref cell, right? Because we want to be able to mutate it. We want it to have it in an immutable way, or a mutable way, right? That's why we do that. Okay. We want a node to own its children, and we want to share that ownership with variables so we can access each node in the tree directly. To do this, we define the vector t items to be a value reference count. We also want to modify which nodes, so that's why we use the ref cell. That's what we just said. Cool. Next, we'll use our struct definition and create one node instance named leaf with the value 3 and no children. The leaf is the end. So if you think of a tree, the leaf is the end. There's nothing further. There's no branches branching off into the leaf. So that's why we call it the leaf. So the leaf is going to be the end, and that's why its children is going to be empty. So that's what we have here. Modify the nodes. Struct definition, create one node named leaf, no children. And another instance named branch with the value 5 and a leaf as one of its children. So branches can have other branches, but they can also end in a leaf. So let's go ahead and do that in main. So here we're going to do let leaf equal, we're going to create a reference counter, new node. What are we going to have? We're going to have a value of 3, and its children is going to be a ref cell. Again, it's got to be a ref cell. It's got to be a vector because that's what we specify the type as. Again, it's not an option, so nil's not an option here. So we're just going to use an empty vector, and we're using the vector macro here to create that vector. So again, we have ref cell new, vector, and then we close that off. What is it complaining about? Let's see, rc new, value 3, children, ref cell, new vector. Let's see. Missing structure field, children. Oh, I spelled it wrong. That's all. Pretty cool though. That's why we're here. Love it. Children. Children. This wouldn't be the first time I've done that. Won't believe it. All right, so then branch is another reference counting node, new node, and here we're gonna have a value of 5, and children will be a ref cell, and this time we're actually gonna have children. So we're gonna say new, we're gonna create a vector using the vector macro, and inside it we're gonna put a clone of the leaf node. So it's just gonna have one child, and in this case the child is gonna be a clone of that leaf node. So we have a leaf and a branch. What is it saying here? Oh, I forgot to put a semicolon. Cool. All right, we clone the reference count node in leaf and store that in branch, meaning that the node in leaf now has 2 owners, leaf and branch. What do they mean by that? They're talking about this node. This node here has 2 owners. Leaf owns it, right? Because that's why this means we own it. And branch owns it because of this. So that's why we use reference counter, right? So we have 2 owners. We can get from branch to leaf through branch.children, but there's no way to get from leaf to branch. You can't go up because the leaf doesn't have a reference to its parent in this case, or the branch, right? The reason is that leaf has no reference to branch and doesn't know they're related. We want leaf to know that branch is its parent. So we'll do that next. And you're already thinking we're having a cycle. If we do that, if we give leaf a way to get back to its branch, we're going to create a cyclical reference, which we know can be problematic. However, we're going to figure out how to do that with weak, right? Adding a reference from a child to its parent. To make a child now aware of its parent, we need to add a parent field to our node struct definition. The trouble is in deciding what type of parent should be. We already know we're going to go with weak because we're in that chapter, but we know it can't contain a reference counter. Why? Because that would create a reference cycle. Leaf parent pointing to branch and branch children pointing to leaf. We'll have that cyclical reference. That's a problem, which would cause the strong count to never be 0, and then we'd have that stack blow up. Thinking about the relationships another way, a parent node should own its children. If a parent node is dropped, its child node should be dropped as well. However, a child should not own its parent. If we drop a child node, the parents still exist. Let's think of an actual tree, all right? Imagine you have a branch, and it's the spring, or it's the summer, and it has a leaf, and I'm going to do the leaf in my hand. So you have a branch and it's got a leaf on it. If the branch falls in the summer, the leaf's going with it. But in the autumn, right, we want to let that leaf fall and the branch isn't going to go with it. Again, leaf can fall on its own, or the leaf can fall with the branch. But the leaf can, in the fall, the leaf doesn't bring the branch with it. You know what I'm saying? Look at these analogies. You're getting like, if you're watching, you're getting some high grade analogies. That's why we're doing it together, right? You could be reading it on your own, but you're not going to get this. Look at this artwork I'm making. Body art. Anyway, so instead of reference count T, we'll make the type of parent use week. Specifically, ref cell week node. Now our node struct definition looks like this. I'm excited. Let's try it out. We're going to do parent. See, now I'm seeing why this stuff is it's pretty cool, right? Parent, so we're going to do ref cell, and we're going to do week, and we're going to give it a node. So here we have, oh, I think I put too many things. Ref cell week, and week contains node, and then we just close that off. That should be right. I probably have to pull in week, right? Yeah. There we go. So what do we have here? Parent is a weak reference. Children is a strong reference because the branch owns the children. And so here we need to declare parent on our leaf. So here what we can do is, so it says here, a node will be able to refer to its parent node, but doesn't own its parent. In listing 1528, we update the main to use the new definition so that leaf node will have a way to refer to its parent branch in this case. Okay, so let's do that. Let's update leaf. So we have our value, we have our children. Let's give it the parent, and the parent is going to be a ref cell new, and we're going to do week new. And we're starting out with nothing. We'll mutate it. We're going to start out pointing it to nothing because we have to create the branch. The branch is created here, right? So we can't reference it here. I mean, we can move the branch up, but then we'd have the same problem with leaf. So it doesn't matter. We're going to have to mutate it, right? And that's why we're using ref cell anyway. You see what I'm saying? I can't just say week new equals branch because branch is defined after the fact. If we moved branch up, we'd have the same problem where chicken before the egg. So that's why we make it a ref cell, because we know that ref cells are mutable and we can just mutate it, which we'll do in a second. So here we're going to instantiate the parent as an empty week, right? I wish I had an empty week. So many meetings, different kind of week. Anyway, so let's go and do in our branch. So, oh, it wants us to print something. So we're going to do print ln leaf parent equals, and again, it's going to be instantiated empty. So we're going to see that it starts out with nothing. Leaf.parent.borrow. We're not borrowing mutable because we don't need to, and we're going to do upgrade. Why are we doing upgrade here? I guess we'll see in a second. Oh, I know why we're doing upgrade, because in order to print it, we need to actually get the thing. And again, it's like looking at the book, right? The week is looking at the book. If it wants to tell you what's on TV, it has to look up, but the TV might be off. You're loving this. You're loving the TV, I know. I know. I love it too. Love it too. All right, so we have value 5 children, and here we're going to give it a parent. Ref cell new week new, and we're not going to add a parent here. Maybe we will, but I don't think it's really necessary right now to have a parent for the branch to illustrate what we're trying to do. And then so here we're gonna mutate that leaf and point its parent to the newly created branch. So first we're gonna do, I'm gonna type it out a little bit. I'm not gonna type it out left to right. I'm gonna type it out how we would think about it. So we definitely know that we want to grab downgrade branch. We'll see what that does in a second. Downgrade branch, because branch is a reference counter. We need to downgrade it to make it a week. That's how we're going to convert it to week. I see if you look here, if you hover, it says creates a new week pointer to this allocation. What does it take? It takes a reference counter and it creates a week pointer, which is what we need. What are we going to do with that week pointer? We're going to set it equal to leaf.value. Sorry, leaf.parent. But again, we can't just set it equal to leaf.parent because leaf.parent is a ref cell, so we have to borrow mute. And again, that's going to give us a reference. So if we want to actually modify the value, we have to dereference it. Home run, right? Now, what does this say here? It says a temporary with access to the borrow is created here. Leaf does not live long enough. Borrowed value does not live long enough. Leaf dropped here while still borrowed. And it's dropped here because we're not using it, I'm pretty sure. And also because I left off that semicolon, so it thought that it's a return. So now we're just going to print ln leaf parent equals, and again we're using our debug. That's why we have the colon question mark. And we're just going to debug. We're going to log here leaf.parent.borrow, borrow that.upgrade, because again we're going to want to convert this weak into a strong. And so if we look at upgrade returns an option. Now, you may ask, why don't we have to handle the value of that option? Well, the reason is because we're just debugging. We're printing. If we wanted to actually use this value, we would have to handle the option with a case statement, right? But we're just printing it so it'll print out whatever the current value is, either some blank or none. But that's just a heads up as to what we're doing there. All right, so let's go ahead and run this. Let me just move it a little bit bigger so we can see what's going on. I'll just move that there. Okay, so let's do clear and cargo run. Okay, so leaf parent starts out as none. That's here because it's none. And then leaf parent here starts out as some, and there you go, some, and then the reference to the branch. Pretty cool. And you can see, look here, that branch even contains children, which is a cyclical reference. So pretty cool. Creating a leaf node looks similar to how creating a leaf node looks in listing 1527, with the exception of the parent field. Leaf starts out without a parent, so we create a new empty weak node reference instance. Pretty cool. At this point, when we try to get a reference to the parent of leaf by using the upgrade method, we get a none value. That's because nothing exists there yet, and it's an option type. When we create the branch node, it will also have a new weak node reference to the parent field because branch doesn't have a parent node. We still have leaf as one of the children of branch. Once we have that node instance in branch, we can modify leaf to give it a weak node. And so that's what's happening here. So we talked about that, where we can now reference, because branch is created, we can now point the parent to it. And that's what we did there. When we print the parent of leaf again, here, I'll read over it again just for clarity. We still have leaf as one of the children of branch. Once we have the node instance in branch, we can modify the leaf. We use the borrow mute method on the ref cell weak node in the parent field of leaf, and then we use the downgrade function to create a weak reference to branch. That's what we saw with downgrade, right? And we saw that upgrade converted it from weak to strong. It's like January 1st, we're all like, we're going to upgrade it ourselves. We're all going to eat healthy and get fit, but not happening. Not for me. When we print the parent of leaf again, this time we'll get a sum variant holding branch. Now leaf can access its parent. When we print leaf, we also avoid the cycle that eventually ended in a Stack Overflow like we had in listing 1526. The weak node references are printed as weak. Awesome. So even though we have a cycle, it's not a problem here. The lack of infinite output indicates that this code did not create a reference cycle. We can also tell this by looking at the values we get from calling reference count strong and reference count weak. So let's do that. So here we say, let's look at how the strong count and weak count values in the reference count node instances change by creating a new inner scope and moving the creation of branch into that scope. By doing so, we can see what happens when branch is created and then dropped when it goes out of scope. The modifications are shown below. So here we have leaf. We're going to go ahead and print this. Oh, we're going to print this within the scope. So we have node. We're going to print this here, just right after leaf. And then we're going to put branch inside a scope here. That's what this block is doing. Branch new. Let's just copy this. putting it in the scope here. And then here we're going to print leaf.parent. Okay, so what we have here is we have our child leaf is created here. We're going to print out the strong and weak references of this leaf. Then we're going to, I'm just keeping this print here. And then what we're going to do is inside this scope, we're going to create a branch. We're going to have the leaf reference the branch as its parent. We're going to print the branch strong and weak count. We're going to print the leaf strong weak count. Then we're going to free up the branch because the scope ends. So branch gets freed up. Then we're going to check and see what the leaf parent is at that point, as well as its strong and weak count. All right. So the key thing is here we added a scope, which should free up the branch at the end of it. So let's go ahead and do cargo run. Of course, I'll get out of your way. Don't worry. And so we have leaf strong equals 1. Then you have weak equals 0. Leaf parent equals none. Branch strong equals 1. Weak equals 1. And so here, let's go over this one by one. So the first one is leaf strong 1, weak 0. So if I look at this, let me just move this down. The reason it's strong as 1 is because it has a strong reference itself. It's a reference count. It's not a weak. The reason it has a weak 0 is it doesn't have a weak reference to the parent just yet. That's why its count is 0. Even though we did this, its count is 0. Then we logged out leaf parent, which is none at first. And then we created the branch and we say that, and then we set the branch as the parent of the leaf. And then we log out branch strong, which is 1 because it's itself. It has its own strong count. And then it has a weak count to its parent here. Wait. Branch strong has weak 1 and weak 1. Why does this not have it? All this has is this here. Okay, so it has its strong reference to its child. Interesting. And then let's see, we have leaf strong 2 here. Interesting. Wait, I'm a little confused. So we start out with leaf strong 1. Okay, so strong equals 1. Weak equals 0. I guess because parent is empty. And then we print out leaf parent, which is none. Great. Then here we print out branch strong equals 1. Its weak reference equals, its weak reference equals 1 because branch references child. It has parent new and it also has child there, which itself has a strong count. And then we have print branch strong, print leaf strong, strong weak, strong is 1 and 0 because, of course, the weak is gone because it got freed up. Interesting. All right, let's read it. After leaf is created, its reference count node has a strong count of 1 and a weak count of 0. In the inner scope, we create branch and associate it with leaf, at which point we print the counts. The reference count node in branch will have a strong count of 1 and a weak count of 1 for leaf parent. That's the weak count of 1 that it has. Pointing to the branch with weak node. Okay. When we print out the counts in leaf, we'll see that it has a strong count of 2 because branch now has a clone of the RC node of leaf stored in branch children. So it gets confusing because it's a cycle. When the inner scope ends, branch goes out of scope and the strong count of the RC node decreases to 0. So its node is dropped. Again, because the weak and strong counts are different, right? The weak count of 1 from leaf parent has no bearing on whether or not node is dropped. So we don't get any memory leaks. If we try to access the parent of leaf after the end of the scope, we'll get none again at the end of the program. The reference count node in leaf has a strong count of 1 and a weak count of 0 because the variable leaf is now the only reference to the reference count node again. So again, it's like the book, the person reading the book, watching the TV. All the logic that manages the counts and value dropping is built into reference count and weak, and their implementations of the drop trait. By specifying that the relationship from a child to its parent should be a weak reference in the definition of node, you're able to have parent nodes point to children nodes and vice versa without creating a reference cycle and memory leaks. Summary. This chapter covered how to use smart pointers to make different guarantees and trade-offs from those Rust makes by default and with regular references. The box T type has a known size and points to data allocated on the heap. Remember, that was key. It's allocated on the heap. The reference count type keeps track of the number of references to data on the heap so that the data can have multiple owners. The ref cell type, with its interior mutability, gives us a type that we can use when we need an immutable type, but need to change an inner value of that type. It also enforces the borrowing rules at runtime instead of compile time. So first, in the beginning, I was saying, oh, reference cell seems like it's used for testing, maybe not real code. Here we saw how it can be used in real code. The book was like, yo, Tom, shut up and finish the book, right? And so we saw how it was used, and that's pretty awesome. Also discussed were the deref and drop traits that all three of these things have, right? Which enable a lot of the functionality of smart pointers. We explored reference cycles that can cause memory leaks and how to prevent them using weak. In this chapter has piqued your interest. So if this chapter piqued your interest and you want to implement your own smart pointers, check out the Rustonomicon for more useful information. Next, we'll talk about concurrency in Rust. You'll even learn about a few new smart pointers. All right, we're only at 10:18, so we got plenty of time. We're going to start this. Another chapter in the books. Woo! Pun intended, right? Chapter 15. Smart pointers, getting a little rough for a minute there, but I think we made it through. All right, concurrency. I'm excited about concurrency. I am. Let's go. What are we waiting for? Fearless concurrency. Handling concurrent programming safely and efficiently is another of Rust's major goals. Concurrent programming, where different parts of a program execute independently, and parallel programming, where different parts of a program execute at the same time, are becoming increasingly important as more computers take advantage of their multiple processors. We talked about this. Historically, programming in these contexts has been difficult and error-prone. Rust hopes to change that. If you've ever tried to do this in other languages, it can be very difficult. I started with Java and it was hard. I use Elixir a lot now and it's really easy because of how languages have evolved. So I'm excited to see how Rust handles this. Initially, the Rust team thought that ensuring memory safety and preventing concurrency problems were two separate challenges to be solved with different methods. Over time, the team discovered that their ownership... sorry, lost my spot. Move my mouse. Over time, the team discovered that the ownership and type systems are a powerful set of tools to help manage memory safely. So they manage memory safety and concurrent problems. So over time, the team discovered that the ownership and type systems are a powerful set of tools to help manage memory safety and concurrency problems. By leveraging ownership and type checking, many concurrency errors are compile time errors in Rust rather than runtime errors. That's great. That means the end users of your code won't see it. You catch it before it's a problem, right? We want that compile time. Therefore, rather than making you spend a lot of time trying to reproduce the exact circumstances under which a runtime concurrency bug occurs, incorrect code will refuse to compile and present an error explaining the problem. As a result, you can fix your code while you're working on it rather than potentially after it's been shipped to production. We've nicknamed this aspect of Rust Fearless Concurrency. Fearless concurrency allows you to write code that is free of subtle bugs and easy to refactor without introducing new bugs. That's pretty sweet. Note, for simplicity's sake, we'll refer to many of the problems in the concurrent rather than being more precise by saying concurrent and or parallel. If this book were about concurrency and or parallelism, we'd be more specific. For this chapter, please mentally substitute concurrent and or parallel whenever you use concurrent. All right. Got it. Many languages are dogmatic about the solutions they offer for handling concurrent problems. For example, Erlang, which is what Elixir runs on, the Erlang VM. Erlang has elegant functionality for message passing concurrency, but has only obscure ways to share state between threads. Supporting only a subset of possible solutions is a reasonable strategy for higher level languages because a higher level language promises benefits from giving up some control to gain abstractions. However, lower level languages are expected to provide the solution with the best performance in any given situation and have fewer abstractions over the hardware. Therefore, Rust offers a variety of tools for modeling problems in whatever way is appropriate for your situation and requirement. Here are the topics we're going to cover in this chapter. First one is how to create threads to run multiple pieces of code at the same time. That's like one of the base use cases, right? Threads for running multiple pieces of code at the same time. 2, Message passing concurrency, where channels send messages between threads. That's when you have multiple threads running that need to send messages. That's an important problem. 3, shared state concurrency, when multiple threads have access to some piece of data. You're probably already thinking, oh, this can create problems, right? Multiple things mutating data, shared piece of state, but it's important. You're going to need that, right? The sync and send traits, which extends Rust concurrency guarantees to user-defined types as well as types provided by the standard library. All right, let's jump in. Let's see, are we going to write some code? All right, so I'm going to go ahead and create that folder now to get ahead here. Let me close this up, and we'll go here and we'll do make dir chapter 16 concurrency. All right, so we're going to do cargo new threads. Oh, I spelled it wrong. Let's remove the other one. All right. Sweet, we're all set up. Okay. In most concurrent operating systems, an executed program's code is run in a process, and the operating system manages multiple processes at once. Within your program, you could also have independent parts that run simultaneously. The features that run these independent parts are called threads, right? So you have threads running independent parts. Splitting the computation in your program into multiple threads can improve performance because the program does multiple tasks at the same time, but it also adds complexity. Because threads can run simultaneously, there's no inherent guarantee about the order in which the parts of your different threads will run. This can lead to problems such as, first one, race conditions, where threads are accessing data or resources in an inconsistent order, deadlocks, where two threads are waiting for each other to finish using a resource the other thread has, preventing both threads from continuing, or bugs that happen only in certain situations and are hard to reproduce and fix reliability. For example, sometimes a thread takes a second, sometimes it takes 2 seconds, and so it's really unpredictable or non-deterministic. Rust attempts to mitigate the negative effects of using threads, but programming in a multi-threaded context still takes careful thought and requires a code structure that is different from that in a program running a single thread. Programming languages implement threads in a few different ways. Many operating systems provide an API for creating new threads. This model, where a language calls the operating system's APIs to create threads, is sometimes called one-to-one, meaning one operating system thread per one language thread. Many programming languages provide their own special implementation of threads. Programming languages provided threads are known as green threads, and languages that use these green threads will execute them in the context of a different number of operating system threads. For this reason, the green threaded model is called the M-to-N model. There are M green threads per N operating system threads, where M and N are not necessarily the same number. So it's not necessarily 1-to-1. It could be, but it might be 2-to-1, it might be 1-to-2, and so forth. Each model has its own, it can't be 2-to-1. Each model has its own advantages and trade-offs, and the trade-offs most important to Rust is runtime support. Runtime is a confusing term and can have different meanings in different contexts. In this context, by runtime, we mean code that is included by the language in every single binary. This code can be large or small depending on the language, but every non-assembly language will have some amount of runtime code. For that reason, colloquially, when people say a language has no runtime, they often mean small runtime. Smaller runtimes have fewer features, but have the advantage of resulting in smaller binaries, which make it easier to combine the language with other languages in more contexts. Although many languages are okay with increasing the runtime size in exchange for more features, Rust needs to have nearly no runtime and cannot compromise on being able to call into C to maintain performance. The green threading M-to-N model requires a large language runtime to manage threads. That's because the language is doing it. It's not doing a one-to-one guarantee of the operating system thread. It has to figure out how many threads per operating system thread and so forth. As such, the Rust standard library only provides an implementation of one-to-one threading. Because Rust is such a low-level language, there are crates that implement M-to-M threading if you would rather trade overhead for aspects such as more control over which threads run when and lower cost of context switching, for example. Content switching. Now that we've defined these threads in Rust, let's explore how to use the thread-related API provided by the standard library. Creating a new thread with spawn. And so this was the part of Rust things that we didn't finish because we hadn't gone through this chapter and it was confusing. So I'm excited to actually go through it now. All right, create a new thread with spawn. So I'm going to open up source here. To create a new thread, we'll call the thread spawn function and pass it a closure. We talked about closures in chapter 13, containing the code we want to run in the new thread. The example in the listing below prints some text from a main thread and other text from a new thread. All right, let's do it. So first we're gonna, up here we're gonna do use standard thread. Then we're gonna use standard time duration. And then we're gonna do, in our function main, we're gonna spawn a thread spawn. And here we have the closure. Remember, this is the function beginning. This is where the arguments would go if we had any. And then here's the body for I in, and we're creating a range here. Print ln high number from the spawned thread. And we're going to pass it I. And then we're going to sleep thread sleep. That's just going to pause the thread for however many milliseconds we provide in this duration here. And we're only using 1 millisecond. From millis does creates a new duration from a specified number of milliseconds. All right, so here it says, what do we have? Expected unit type, but because we didn't put a semicolon. All right, and then for I in a range of 1 to 5, we're gonna do same thing, print high number from main thread. And then we're gonna do thread sleep duration from millis, and we'll do 1 there. All right. Note that with this function, the new thread will be stopped when the main thread ends, whether or not it is finished. The output from the program might be a little different every time, but it looks similar to the following. All right, let's check it out. So here we have high number 1, main, 1 from spawn, 2 from main, 2 from spawn, 3 from main, 3. So let's try running it again. This time we actually made it to 5. This time we didn't make it to 5. We didn't make it to 5. Didn't make it to 5. There we made it to 5 again. So it's different every time. So this thread stopped when this thread completed. So pretty cool because the function ended, right? The calls to thread sleep force a thread to stop its execution for a short duration, allowing a different thread to run. The threads will probably take turns, but that isn't guaranteed. It depends on how many operating system schedules the threads. It depends on how your operating system schedules the threads. In this run, the main thread printed first, even though the print statement from the spawn thread appears first in the code. And even though we told the spawn thread to print until I equals 9, it only got to 5 before the main thread shut down. If you run this code and only see output from the main thread or don't see any overlap, try increasing the numbers and the ranges to create more opportunities for the operating system to switch between threads. Pretty cool. Waiting for all threads to finish using join handles. The code in listing 16.1 not only stops the spawn thread prematurely most of the time due to the main thread ending, but also can't guarantee that the spawn thread will get to run at all. The reason is that there is no guarantee on the order in which threads run. We can fix the problem of the spawn thread not getting to run or not getting to run completely by saving the return value of spawn thread in a variable. The return type of thread spawn is join handle. A join handle is an owned value that we can call the join method on it. We'll wait for its thread to finish. Listing below shows how we can use join handle to basically exhaust that thread, right? Join handle the thread we created below and call join to make sure the spawn thread finishes before the main exits. So let's do that. Let handle So it says here join handle. We have a join handle. And here we're going to do handle.join.unwrap. And let's run it. And you can see we actually were able to finish. We got all the values from the spawn thread. Again, 10's non-inclusive, that's why. So you can see we made it to all the way to 4 on the main thread, and then the spawn thread made it to 10. So pretty cool. Calling join on the handle blocks the thread concurrently running until the thread represented by the handle terminates. Blocking a thread means the thread is prevented from performing work or exiting. Because we put the call to join after the main thread's for loop, running below should produce similar output similar to this, and that's exactly what we got. The two threads continue alternating, but the main thread waits because of the call to handle join and does not end until the spawn thread is finished. But let's see what happens when we instead move handle join before the for loop of main like this. I'm just going to put a comment. When placed here, the entire thread, spawn thread will run. Let's try moving up here. And so here you can see it executes the spawn thread completely first before even trying the main thread. Whereas before, it kind of alternated because we kicked that off. So pretty cool. The main thread will wait for the spawn thread to finish and then run its for loop, so the output won't be interleaved anymore, as shown below. Small details such as where join is called can affect whether or not your threads run at the same time. Pretty cool. Using move closures with threads. The move closure is often used alongside thread spawn because it allows you to use data from one thread in another thread. In chapter 13, we mentioned we can use the move keyword before the parameter list of a closure to force the closure to take ownership of the values it uses in the environment. This technique is especially useful when creating new threads in order to transfer ownership of the values from one thread to another. Notice in the listing below that the closure we pass to thread spawn takes no arguments. Yep, we have no arguments here. We're not using any data from the main thread in the spawn thread's code. To use data from the main thread in the spawn thread's closure must capture the values it needs. So the listing below shows an attempt to create a vector in the main thread and use it in the spawn thread. However, this won't work yet, and we'll see that in a moment. So let's try that out. Let's do let v equal vec. Let's move this up here. Equal vec 1, 2, 3. I'll do let handle 2 equal thread spawn. Now I'm going to go ahead and give it a closure that takes no arguments again. And the closure that takes no arguments is going to try to print out that vector using the debug display. And then we'll do handle 2.join.unwrap. So what are we doing here? Our closure here, and you can see it's not going to compile. To force the closure to take ownership of V, we must use the move keyword. So it doesn't take ownership here, so it's not allowed to use it. The closure uses V, so it will capture V and make it part of its closure's environment. Because thread spawn runs this closure in a new thread, we should be able to access V inside the new thread, but when we compile, we get the following error. Function requires argument type to outlive static. Rust infers how to capture V, and because println only needs a reference to V, the closure tries to borrow V. However, there's a problem. Rust can't tell how long the spawn thread will run, so it doesn't know if the reference to V will always be valid. So below, we see a scenario that's more likely to have a reference to V that won't be valid. So here you can see if they drop V, oh no, V will no longer be valid, right? if we're allowed to run this code, there's a possibility the spawn thread would be immediately put into the background without running at all. The spawn thread has a reference to v inside, but the main thread immediately drops v, using the drop function we discussed in chapter 15. Then when the spawn thread starts to execute, v is no longer valid, so a reference to it is also invalid, which would cause that problem. By adding the move keyword before the closure, we force the closure to take ownership of the values it's using, rather than allowing Rust to infer that it should borrow the values. So it's being explicit. It's saying, hey, you should take ownership. The modification in the listing below will compile and run as we intend. So let's try it out. And we saw that it told us with our inference that we should use move. So I'm just going to go ahead and run this. Let me just pop out of your way for a second. And there you go. Here's a vector, 1, 2, 3. It spawned in there. So pretty cool. It was able to run. It was able to use v, even though v was declared outside of here. What would happen in the code in listing 1614 where the main thread called drop if we use a move closure? Would move fix that case? Unfortunately, no. We would get a different error because the listing in 16.4 is trying to do isn't allowed for a different reason. If we had to move to the closure, we would move v into the closure's environment, and we can no longer call drop on it in the main thread because it's been moved into the closure. Does that make sense? We learned about that early on. Rust's ownership rules have saved us again. We got an error from the code in listing 16.3 because Rust was being conservative and only borrowing v. Nathaniel Bumpo in the chat says, join handle join will also return the value that the closure run by the thread returns. Oh, nice. So join handle join here will return the value that the closure here runs by the value that the closure run by the thread returns. So got it. So the value of the closure run by the thread, this closure returns. So it'll actually return the value that this returns. Pretty cool. Thanks, Nathaniel. That's awesome. Rust ownership rules saved us again. We got an error from the code. Rust was being conservative and only borrowing v, but we've explicitly told it to move v. By telling Rust to move v to the spawn thread, we're guaranteeing that to Rust that the main thread won't use v anymore. Just like we learned early on, right? If we change listing 1614 the same way, we're violating the ownership rules when we try to use v in the main thread. The move keyword overrides Rust's conservative defaults of borrowing. It doesn't let us violate the ownership rules. With a basic understanding of threads and the thread API, let's look at what we can do with threads. All right, I'm down. Yeah, I think we make it through most of this. We got a few minutes left. All right, using message passing to transfer data between threads. Let's see. Our increasingly popular approach to ensuring safe concurrency is message passing, where threads or actors communicate by sending each other messages containing data. Here's the idea in a slogan from the Go language documentation. Do not communicate by sharing memory. Instead, share memory by communicating. Ooh. One major tool Rust has for accomplishing message sending concurrency is the channel, a programming concept that Rust standard library provides as an implementation of. You can imagine a channel in a programming language as being like a channel of water, such as a stream or a river. If you put something like a rubber duck or boat into the stream, it will travel downstream to the end of the waterway. A channel in programming has two halves, a transmitter and a receiver. The transmitter half is the upstream location where you put the rubber ducks into the river. So the transmitter is where you put the rubber ducks in. And the receiver half is where the rubber duck ends up downstream. One part of your code calls methods on the transmitter with the data you want to send, and the other part checks the receiving end for the arriving messages. A channel is said to be closed if either the transmitter or receiver half is dropped. Here we'll work up to a program that has one thread to generate values and send them down a channel, and another thread that will receive the values and print them out. We'll be sending simple values between threads using a channel to illustrate the feature. So simple values. Once you're familiar with the technique, you could use channels to implement a chat system or a system where many threads perform parts of a calculation and send the parts to one thread that aggregates the results. That's pretty sweet. Okay, in listing 16.6, we create a channel, but do not do anything with it. Note that this won't compile yet because Rust can't tell what type of values we want to send over the channel. All right, so I'm going to create a new folder for this. So we'll do cargo new message passing. All right, pull that up there. All right, so we have this here. We're going to go ahead and import standard library, sync, MPSC, and in our function main, we're going to have a tuple, txrx equals MPSC channel. All right, and you can see here, sender, receiver, or transmitter, receiver, right? Okay. We create a new channel using the MPSC channel function. MPSC stands for multiple producer, single consumer. So multiple producer, single consumer. In short, the way Rust standard library implements channels means a channel can have multiple sending ends that produce values, but only one receiving end that consumes those values. So multiple producer, single consumer. So again, you have a lot of things putting rubber ducks in, but the rubber ducks can only end up in one place. Got it. Imagine multiple streams flowing together into one big river. Everything sent down any of the streams will end up in one river at the end. We'll start with a single producer for now, but we'll add multiple producers when we get this example working. The multiple producer single consumer channel function returns a tuple, the first element of which is the sending end, and the second element is the receiving end. The abbreviations TX and RX are traditionally used in many fields for transmitter and receiver respectively, so we name our variables as such to indicate each end. We're using let statement with a pattern that destructures the tuples. That's what we're doing there. We'll discuss the use of patterns in let statements and destructuring in chapter 18. We're pretty familiar with destructuring, but interesting. Using a let statement this way is a convenient approach to extract pieces of a tuple returned by the multiple producer single consumer channel. All right, let's move the transmitting end into a spawn thread and have it send one string so the spawn thread is communicating with the main thread as shown in the listing below. This is like putting a rubber duck in the river upstream and sending a chat message from one thread to another. So let's go ahead and do that. So we're going to pull in thread. We have our channel. We're going to spawn a thread. We're going to use our closure. We're going to take ownership with our move closure. All right, we're going to move ownership into our closure here. Value equals string from hi. So we just have a simple string there. And then we're going to do tx, which again is the transmitter, send, tx.send value, and unwrap. If we look at what unwrap does here, we can see that it returns the contained OK value consuming the self value. Remember, it's like the when we have the result, right? So it operates on a result, and it gives you the OK value. If it fails, it'll panic, right? So let's go ahead and put a semicolon there and there. Okay, so again, we're using thread spawn to create a new thread, and then using move to move transmitter into the closure so the spawn thread owns the transmitter. The spawn thread needs to own the transmitting end of the channel to be able to send messages through the channel. The transmitting end has a send method that takes the value we want to send. The send method returns a result type. So if the receiving end has already been dropped and there's nowhere to send a value, the send operation will return an error. In this example, we're calling unwrap to panic in case of an error. But in a real application, we would handle it properly. And we've seen that, right? We'd handle the OK case or the error case. In listing 16.8, we'll get the value of the receiving end of the channel in the main thread. This is like receiving the rubber duck from the water at the end of the river, or like getting a chat message. All right, so let's do that. We have our thread here, and here we're going to do let received equal rx.receive.unwrap, because again, that's going to return a result type. And then we're going to go ahead and print ln got comma received. So we're using the receiver to receive that value. The receiving end of the channel has two useful methods, receive and try receive. We're using receive, short for receive, which will block the main thread's execution and wait until a value is sent down to the channel. Once a value is sent, receive will return it in a result. When the sending end of the channel closes, receive will return an error to signal that no more values will be coming. The try receive method doesn't block, but will instead return a result T immediately, an OK value holding a message if one is available, or an error if there aren't any messages at that time. Using try receive is useful if this thread has other work to do while waiting for messages. We could write a loop that calls try receive every so often, handles messages when it is available, or otherwise does other work for a little while waiting until it's ready to check again. We used receive in this example for simplicity. We don't have any other work for the main thread to do other than wait for messages, so blocking the main thread is appropriate. When we run the code, we'll see the value printed from the main thread. All right, let's run it. And there we go, got high, pretty cool. Perfect. Channels and ownership transference. The ownership rules play a vital role in message sending because they help you write safe, concurrent code. Preventing errors in concurrent programming is the advantage of thinking about ownership throughout your Rust programs. Let's do an experiment to show how channels and ownership work together to prevent problems. We'll try to use a val value in the spawn thread after we've sent it down the channel. Try compiling code in listing 16.9 to see why this code isn't allowed. All right, let's try it. So we have val here. We're sending val. At this point, we're going to try to print it here. Right away, we don't need to compile. We just hover. It says borrow of moved value val. Val borrowed here after move. Where did it get moved? It got moved to here. So let's put that here. And let's say the below won't work. Uncomment to find out why. Oh. Here we try to print val after we send it downstream to the channel send. Allowing this would be a bad idea. Once the value has been sent to another thread, the thread could modify or drop it before we try to use the value again. Potentially, the other thread's modifications could cause errors or unexpected results due to inconsistent or non-consistent data. However, Rust gives us an error if we try to compile the code in the listing below, which we saw. Our concurrency mistake has caused a compile time error. The send function takes ownership of its parameter, and when the value is moved, the receiver takes ownership of it. This stops us from accidentally using the value again after sending it. The ownership system checks that everything is okay. So we're getting great benefits here at compile time. Sending multiple values and seeing the receiver waiting. The code in the listing below compiled and ran, but it didn't clearly, the one we did prior, 16.8, compiled and ran, but it didn't clearly show us that two separate threads were talking to each other over the channel. In listing 16.10, we've made some modifications that will prove the code in the listing above is running concurrently. The spawn thread will now send multiple messages and pause for a second between each message. All right, and we'll see that. We'll see the way it's going to be printed. All right, let's do it. So we have our channel. We have our thread here. We're going to do vals. Let me just comment this out. Let vals equal, we're going to use the vector macro. It's going to contain string from hi from the thread. Pretty cool. And then we're going to do for val in vals tx.send val. Again, we're sending it, it's taking ownership, so we can't use val again. And then we're going to sleep, and how long? We'll do it for 1 second. So instead of using for milliseconds, we're going to do duration from second 1. So we should see it print every 1 second. And then here, instead of just doing receive.unwrap, we're going to do, let's cut that out. We're going to do for received in Rx, print ln got received. So apparently we can iterate over our Rx here to get that instead of just doing Rx.receive. I before E except after C. All right, let's try it out. Move out of your way here. Hi from the thread. Pretty cool. Pretty cool. Let's see it again. I know you all want to see it again. Hi from the thread. Nice. Hell yeah. This time the spawn thread has a vector of strings that we want to send to the main thread. We iterate over them each individually and pause between each by calling thread sleep function with the duration of 1 second. In the main thread, we're not calling the receive function explicitly anymore. Instead, we're treating the receiver as an iterator. For each receive value, we're printing it. When the channel is closed, the iterator will end. When running the code, we see the following output, which we saw. But we don't have any code that pauses or delays in the for loop in the main thread. We can tell that the main thread is waiting to receive values from the spawn thread. Creating multiple producers by cloning the transmitter. So we're going to create a few producers of information. Earlier, we mentioned that multi-producer single consumer was an acronym for multi-producers. Well, let's put multi-producer single consumer to use and expand the code in the listing below, or the listing we just did, to create multiple threads that all send values to the same receiver. We can do so by cloning the transmitting half of the channel, as shown in the listing below. So we're cloning the transmitter. So let me do this. Let me just comment this out. And I'm going to create another one. Simple single producer, single consumer. That's that. And then here we'll do our new main. We'll copy our function here, paste it here, uncomment it out, and modify it. So we have TX is, this channel stays the same. We have TX1. So we're going to do TX1 equals multi-producer, single consumer, sender, clone, and we're going to clone TX. So we're going to clone that TX that we received. So now we have TX1, which is a clone of that, which is pretty cool. And then what are we going to do with it? Well, inside our thread here, we have 4 val and vals. We're going to do TX1.send. And then here, we're spawning a second thread. So I'll just copy this. So again, this thread is using TX1. I'm going to go ahead and spawn a second thread here. This thread is going to use the regular TX, and we're going to send a different thing here. Say more, like they have here, messages for you. And so here we have received, print, got, received. So let's run this and see what happens now. Pull that up a little bit, we have more room. Hi, more from messages, the for thread you. So hi from the thread, more messages for you. So we're producing, it's producing interspersed. And if we run it again, we'll see it's still doing the same thing because of that wait. So it works out really well. Hi from for. So here you can see it's not necessarily going to do 1 and 1, right? So instead of hi from the thread, we have more messages for right away. So you can see that they're not guaranteed to run in the exact order, which is pretty cool. I mean, it's cool to see that illustrated. This time, before we create the first spawn thread, we call clone on the sending end of the channel. This will give us a new sending handle we can pass to the first spawn thread. We pass the original sending end of the channel to the second spawn thread. This gives us 2 threads, each sending different messages to the receiving end of the channel. When you run the code, your output should look something like this. You might see the values in another order. It depends on your system. This is what makes concurrency interesting as well as difficult. If you implement with thread sleep, giving it various values in different threads, each will be more non-deterministic and create different output each time. Now that we've looked at how channels work, let's look at a different method of concurrency. All right, we are at almost 11 o'clock, so we are going to end it here for today. Thank you for hanging out in the chat if you've been a part of it. This is really fun. This is one of the parts I was very interested in, was the concurrency side of things. I always find it very fascinating. Smart pointers was also super interesting. It's going to be really cool at the end of this. Again, we're going to get there. When we get to chapter 20, we are going to be building a multi-threaded web server. I'm excited about that. I know it's going to be fun. It's going to be challenging. It's going to be cool. I hope you're all here for the ride. If you're watching on YouTube, I appreciate it. Thank you always for that. Again, if you want to check out any of the past videos, this video will be posted tomorrow, but you can check out all the past videos there. If you wanted to do the smart pointers part 1, it's right here. We mentioned that a few times. Follow on Twitter, get updates when I go live. I'll also post if I post any other content. I'm going to be pushing this code up to the Learn Rust Live repo. And again, we will pick up with shared state and concurrency next week. So thank you again for watching. Those of you watching on YouTube, really appreciate it as well. You know, whatever speed you're watching on, 1.5 speed. Oh, we got Esprit 4 RT, which would be pronounced Esprit Art if you're using Leet. Esprit Art. Awesome. Sorry if I butchered your name. Thank you for the follow. Always appreciated. But yeah, definitely check it out. If you're watching on YouTube, hit that like, the subscribe. It always helps. If you're following on Twitch, happy to have you. And if you haven't checked out the live stream yet, and you've been mostly checking it out on YouTube, if you're around on a Tuesday, 9 p.m. to 11 p.m. Eastern Time, hop in. You can ask questions live, and then you can go watch yourself ask the questions live on the YouTube channel. So thank you so much. Hope you're enjoying our journey on becoming Rustaceans. We've made it through chapter 15. We're on 16 now. We've made it very far. We're going to keep going with it. It's been really enjoyable, and it's been a fun ride. Thanks to all of you. Thanks for the great comments in the chat as well in Twitch and on YouTube. We've been getting some awesome comments. Feel free to ask questions. Happy to answer them. It's just been really cool seeing everyone contribute a little bit. So thanks, everybody. Hope you all have a great night. Take care.